So, who knows what a vector is? A straight line. Yeah. Okay, write this down. Yeah. Say that again, Skyla.
The name of a supervillain?
Yeah. Do you remember what his name means?
I'm trying to think of who it was even.
His name is Vector.
Okay, that's what I was thinking. Yeah. Because I can't remember why. Doesn't he say when they're
It's directly related to this definition. He even says it. Yeah.
What does he say? We should look it up and watch it.
It says it's a straight line with both direction and magnitude.
There you go.
I mean, I said it like 4 different times.
Do you want a replay? We can get a replay on that. What?
Yeah, that sounds good.
Hold on, let me read. What? Oh, sorry. Quantity. Don't ask math teachers to write.
Magnitude is totally. Sorry, it's multi.
Magnitude. Magnitude.
There's no N.
There is an N. That is an N. Magnitude.
It's an
Oh,
N.
I see that.
M-A-G-U.
I see
Mag-
it too, but I think
Magnitude.
Yeah, we all know what you meant. I think you need to take a
I think you guys need to take a reading class. Magnitude and direction. Okay. So, I'm going to draw a vector. Are you ready?
I'm so confused. I don't know what
So, that's a picture of a vector. It looks like a straight line. It starts at a single point, which is called the initial point, by the way. Okay, and sometimes you might refer to it as the tail of the vector. Okay, and it goes to another point, which is where this arrow is, which we're going to call the terminal point. And sometimes I'll call that the tip, just so you know. All right, so I just told you that a vector represents a magnitude and a direction. Two pieces of information, right? Right. Okay, so the first part of this is going to ask you, is the scenario a scalar or a vector? Okay, so who remembers what a scalar is? It's just one number. Okay, so a scalar is one number, so a vector is going to be basically two things, a magnitude and a direction. Okay, so here is an example of a vector. Okay, so the velocity of a football is a vector that describes both the speed. Okay, so do you think that the speed is the magnitude or the direction? Zach, Jeff, zip it. Thank you. Okay, that's in reference to the magnitude. Okay, so the speed is like the magnitude. Okay, and the direction of the ball. Okay, so perhaps the ball was thrown at a 45-degree angle or something. Okay, with initial velocity. Okay, so you tell me now. I'm going to give you an example. I'm not going to write this down. I'm going to say this verbally if that's all right with you. If you want to write it down, that's up to you. Okay, so my example number 1. Is this a scalar or a vector? A boat traveling at 15 miles per hour.
Vector.
Okay, let's have a vote. Who thinks that it is a scalar? Who thinks that it is a vector? Okay, the correct answer is that it is a scalar. Okay, we only know the speed of the boat.
But it has to
We
be going
do
in
not
some
know the direction.
But it's going in a direction.
That is true. Unless you know what it is, you can't assume it. Because we all know what you become if you assume something. Okay, example number 2. Ready? A hiker walking at 25 paces due west.
Vector.
Okay, that is a vector. We know how fast, and we know exactly which direction. What's that?
That's all we're doing.
Oh, no.
Wait, so what's a scalar?
Just a number. One number. Single number.
Scalars either have the speed or the direction. So it's vector.
Okay, what about this scenario? A person's weight on the bathroom scale.
Like a person's weight.
Weight.
It's a scalar.
Okay, so if I weigh 100 pounds,
That's not.
is that a scalar or a vector?
Unless you count gravity.
Do we know the direction?
Down.
Yeah, we know the direction. When we know that it's related to gravity, we know the direction. Okay, so a person's weight is a vector. People who are in physics, weight is considered a force. Forces are vectors, right? What's that? Right, negative, yes. Mm-hmm.
That's terrible.
Force, right. Yes. Okay. What about this example? We have a car traveling 60 miles per hour, 15 degrees east of south. Scalar or vector? That one's definitely a vector. We had a speed, we had a direction, very straightforward. Okay, what about this last example? If a child is pulling a sled with a force of 40 newtons.
Force. Vector.
Do we know the magnitude and do we know the direction? It's a scalar. We know that there is a force involved, but we do not know which direction the child is pulling. That is imperative to understand a vector. We got it? Direction. Must know direction. All right. That was understanding, part 2. We are going to multiply scalars by vectors. Let's see, multiply. Oh, I wanted a different color. Multiply. That's an M. Okay, so I'm going to show you 2 ways to do this, by the way. I'm going to show you how to do it graphically, and I'm going to show you how to do it numerically. You're going to prefer the numeric version, but you have to understand the graphic version because it directly relates. Okay, so let's say for an example, it's going to ask us to draw 3x minus 3/4 y. Okay, and they give us 2 vectors. They say that the x is roughly this length, and it looks like it goes straight to the right. And the y vector is going to be a longer one that looks like about a 45-degree angle. Okay, how do we draw vectors together? Okay, so let's start with interpreting 3x. If I was going to draw 3x, how do you think I would draw that? Think of it very literally. How many x's am I going to draw? 3 of them. Okay, so if one x is about that distance, what I'm going to do is I'm going to draw them tip to tail, and it's going to look like it has a length of about 3. Okay, so it's going to look like this. We're going to have, that's 1x, 2x, 3x. Okay, so that's 3x. Everybody understand that? Tip to tail. Do you see what I mean by tip to tail? Okay. So now if I was going to draw 3/4 of y, how would I draw 3/4 of y? Roughly less, right? Three-quarters of it. Okay. So what I'm going to do is I'm going to combine these two vectors. Okay. So if I'm subtracting, do you think I'm going to go tip to tail, or am I going to go tail to tail, or tip to tip? What? What'd you say?
I don't know how to do this. I never learned this.
Okay, so that's a guess. Go ahead and just guess. So obviously I just did tip to tail when I did those three together, right? Okay, so if I'm going to add vectors, do you think I go tip to tip, or do you think I do tail to tail? Tail to tip, that's adding. Tip to tail is adding.
Tail to tail.
Subtracting is tip to tip. Tip to tip. Okay, so what I'm going to do, see how I'm at the end of this first tip? Okay, so this is where I'm concluding this. So I'm starting here. This is the distance of 3x in direction. So now I'm going to use a 45-degree angle, and I'm going to do a vector that's 3/4, so about that. So there's going to be my endpoint, but I'm going to put the tip right here. Okay, so tip to tip. And let me try that one more time. That didn't look good. Whew. That didn't look like 3/4 to me. There we go. Okay, so this is 3/4 of y. Okay, so now the result, I'm going to draw this in green, is going to go from the start to the finish. Okay, basically creating a triangle. Okay, so the resultant vector, good lord. Sorry, I cannot not write when I'm standing, I guess. It's just the green one. Okay, so technically what you need to understand is that a vector can be taken off of a grid and I can move it anywhere. Okay, so as long as my resultant has this angle and this distance, then that is the result.
And it's not exact.
Well, I can move a vector anywhere.
Yeah, but
Well, it would be exact if I had like a ruler. And if I had actual values for my x and y, I can figure out exactly what it would be. But since they're just going to have you draw off of another one without using a ruler and a compass, we're just going to kind of freehand it. So to the best of our ability. So let's do one more. Let's do 2. So let's do m minus 1/4 of p. Okay, so let's say my m kind of goes off this direction. And my p goes this direction. They look about the same length, but one goes like that one looks like 120 degrees. That one looks like maybe 30 degrees. Okay, so how do I draw this? I start with what? With my m. So my m is just m, so I'm just going to draw an m. Okay, so there's m. Okay, and then since I'm minusing, what am I going to do? Tip to tip. And how much of p am I going to draw? Just 1/4. So just a little bit of p. So like that much is p. So that's going to be 1/4 of p. Okay, so my resultant vector, I'm going to draw my resultant in green. Starts from the initial points where I started my m and goes to the end of my p that creates the triangle. Okay, so that's my resultant vector. I always circle mine so you know which one it is. Sure, if you labeled it so I know which one is R, yeah, that's fine. Okay, so we're good with drawing vectors like that. That's pretty easy. I'm missing a page, I think. Oh wait, maybe this is all we do in this chapter. Okay, part 3, I guess. I'm going to give you some definitions. These should be probably pretty obvious to you. Let's do this in P. Okay, they use parallel vectors. So what do you think you know about parallel vectors? They're two vectors that are parallel. So if you think of it in terms of magnitude and direction, though, they have equal direction. Does it matter about the magnitude? No. Okay, so the only thing that we have to know is that they have the same direction. Okay, can it be possible for parallel vectors to be in opposite directions? Okay, so like these are parallel, but what if one is pointing this way? See what I'm saying? So like 180 degrees difference, right? Okay, so that would be parallel, that would work. Okay, so we can say parallel vectors have same or opposite. Okay, so you might give yourself a little note what is meant by opposite, so like 180 degrees difference. Direction. Okay, so, and you could even add on there, but it doesn't necessarily have to be the same magnitude. Okay, so FYI, you would write that as, let's say if we had A and B as our two parallel vectors, you write that notation like that. So you see those two little parallel lines. Okay, if two vectors are equivalent, what would you know about two vectors that would be equivalent? Same magnitude and same direction. Okay, so they would have to have exactly the same magnitude and same direction. Okay, so you would write that as A is equal to B. So has anybody noticed how I'm writing vectors, by the way? Yep, A's and B's. You can use any letter, but what kind of letters am I writing? Lowercase. Okay, so we use lowercase letters to represent vectors. Yep, and there'll be lines. Yep, so when we get to more notation stuff, we'll start using different, okay? And then opposite vectors, what would you say an opposite vector is? Huh? 180 degree difference on the direction. What about magnitude? Same or what? On the magnitude? So, yep, they would have to have same magnitude. So opposite vectors, they have to have the same magnitude, so same force, pushing against each other, but opposite directions. So what would you know about two vectors that are pushing against each other? So if I add two opposite vectors, what will they equal? 0. Okay, so if you're adding them, they would equal 0 because they would like cancel each other out. Okay, so the other thing they add into this section is they do bearings. So let me see how to do this real quick. So you guys know what bearing is, right?
Like bearing a child.
So no. That's science class. In math and vectors, bearing is directions. Directions. Okay, so like north, south, east, west bearings. Okay, so there's 3 different kinds of bearings. I'm going to start with a quadrant bearing. Why don't you set it here so I can keep good track of it? Thank you. What? BEA, yes. I did spell that correctly. That's how you spell bearing. BEA, like a bear. Does? BEA.
That's definitely an E, Mari. I can't, obviously you didn't take it.
Direction. O, measurement. Between. Oh my gosh, that was an F. Hold on, I did spell that wrong. Draw that wrong. 0 degrees and 90 degrees. Okay, notice I'm saying degrees as opposed to radians. Okay, so bearings will always be in degrees, possibly in degrees, minutes, and seconds. Okay, so east or west of the, oops, north-south line. Okay, so I'm going to do example for that because I don't think that definition is very clear. Okay, so quadrant bearing. So let's say we were going to draw south 35 degrees east. Okay, so that's an example of the way you would see a quadrant bearing. Okay, so the south or north always goes first, and then the east or west goes last. Okay, so if I'm going to draw this, you know your bearings. You have north, south, west, and east. Okay, so this is going to be, what's that? So this is going to be 35 degrees off of the south in the direction of east. Okay, so if this is south, this angle right here is going to be 35 degrees, okay, in the direction of east. So it's always off of either the north or south. That makes sense? Do I need to do another example for that for that to be clear? Okay. The second one is called true bearing.
We're almost on those.
Almost. This is probably one of the sections that requires the most writing. Okay, so this is kind of an interesting one to me. Okay, so they have true bearing, and true bearing is always measured off of north. Okay, so if you were going to have a true bearing of 25 degrees, notice the way that it's written. Okay, so there's 3 digits. Okay, so that one would look somewhere like, so if this is north, and if you go clockwise, okay, clockwise is that direction, that would be the 25-degree angle. Okay. So things that they're going to do for this is they'll say draw the vector, and they'll say A is equal to 20 feet per second at a bearing of 0, 30 degrees. Okay, so if I was going to draw that one, okay, I draw my little compass. I have north. Okay, so what direction am I going to go? 30 degrees to the right. Perfect. Okay, so I would say this angle is 30 degrees. Okay, and then basically the 20, what is the 20 telling us? The magnitude. Okay, so in reference to the way I draw this, it's basically telling me that the length of the vector is 20 units. Okay, so it has this angle and it has this magnitude, which is represented as the length of the vector. Good there? Last one? I don't know why there's so many different types of bearings. I don't know. It's a big world, I guess. The last one is horizontal. I'm just going to do an example for this one. I'm going to say 3. So let's say we have vector V is 75 pounds of force at 140 degrees to the horizontal.
75 pounds.
75 pounds. Okay, so 75 pounds is the magnitude of the vector. Okay, so horizontal bearing is basically like the idea of using the unit circle. Okay, so the horizontal is like the terminal side that we used when we did the unit circle, 0 degrees. So if I was going to draw 140 degrees from 0, where about would it lie? Yeah. Okay, so it'd be somewhere over here. Okay, so the angle to 140 would be off of that terminal side. So this is 140. This is where you see it the most.
That way, not like
Counterclockwise? Why does the unit circle go counterclockwise? Well, that's why it's horizontal. Well, it comes from the unit circle off the horizon. Why does it go counterclockwise? I don't know. 'Cause.
Oh, I got you.
Okay, so the magnitude of that would be, whoa, excuse me, 75 pounds. So 75 units, distance is 75. You hit everything? So should I do like an example with all this, or you just want to do it when you get to it?
Let's do it.
Feel like you kind of got it and you might be able to figure it out without me doing an example? Okay, I'm going to let you try. Okay, so you have page 488, and it's 2 through 48 evens. It's like drawing vectors. It's not hard.